Before we look at use cases, let's take a quick tour of the Hazelcast platform. Hazelcast combines a stream processing engine with a fast data store, both atop a distributed architecture. Briefly, a distributed system is one that runs across a cluster of multiple systems, either physical servers or virtual machines in a cloud. Both data and processing are distributed across the memory and CPU capacity of the entire cluster. This distribution is part of the function of the architecture and occurs automatically, which means that you can scale the cluster size up or down as needed without manually redistributing data or applications. Elasticity also provides fault tolerance. The system is built to adapt to changes in the cluster, so the removal of a cluster member does not interrupt operations. The Hazelcast platform runs inside a Java virtual machine. As long as the underlying operating system supports Java, you can run Hazelcast on any system, although for production we recommend Linux. Running as a JVM also allows you to use Java orchestration tools like Spring for managing and maintaining your applications, in addition to tools like Kubernetes that orchestrate at the Linux level. Fast data storage provides in-memory caching of data for performant access by applications. Data is stored using familiar data structures like maps and lists that have been optimized for operation across a distributed system. The most commonly used data structure is the distributed map, a key value store that you can access with the Java Map API. The value field can be any data type, a POJO, or a JSON object. You can also use SQL in any of our supported clients to read, search, and write data to the key value store. Fault tolerance is provided by replication of the data between cluster members, always ensuring that the primary and the backup copy of data are stored on different cluster members. If a cluster member is removed, backups take over instantly, and new backups are created and redistributed across the remaining cluster members. This elasticity also applies when adding cluster members to increase capacity, allowing you to use tools like Kubernetes to dynamically size your cluster according to workload. And if an entire data center goes down, the Hazelcast platform also offers features for seamless redundancy between data centers, with data replication and automatic client failover. The Hazelcast platform offers distributed computing that is co-located with your data. You can run Java code against your in-memory data for fast computations. A simple example is calculating rate of return. You could have an application client download all the return data, then calculate the rate of return locally, but this is inefficient. It adds latency with the data download, and it relies on the CPU of the application to do all the computation. Hazelcast enables you to run your computations within the cluster, taking advantage of the multiple CPUs to run computations in parallel, and eliminating the latency of transferring your raw data across the network. Another advantage of co-located computing is that it is co-located, meaning that access to the data is handled within the system. This is critical when processing orders or updating balances. It prevents ABA write problems and provides better overall consistency. Co-located computing can also be deployed reactively through the use of listeners. Listeners monitor changes to your data and launch programming in response to those changes. Client applications can receive instant updates without any need for polling. The event processing engine within the Hazelcast platform is optimized for working with streaming data and providing real-time computation capabilities. This engine is also reactive programming, but instead of responding to changes in stored data, it responds to events as they are delivered to the platform. Financial services customers are using this engine anywhere a real-time response is needed, whether it's fraud detection, monitoring and responding to market changes, or offering customers loans while they're still at the ATM. The programmer writes a pipeline, which is a graph of steps that the data must flow through. Hazelcast takes that pipeline and parallelizes it across the cluster. As events arrive, they use the fastest available path through the cluster. Because these jobs run on top of the distributed architecture, they inherit the same resiliency and elasticity that Hazelcast provides for stored data. You can use this elasticity to dynamically deploy event processing microservices where and when needed. Hazelcast has also incorporated mechanisms to ensure that individual events aren't lost, even if the job starts or stops. Local snapshots combined with replayable sources ensure that you don't miss a single bit of data. We've included support for Python, so you can use a distributed job to run your machine learning inferences without having to change your coding platform. Hazelcast will spin up the Python instances for you, load all needed packages, and run the orchestration across the distributed system. The non-blocking architecture of the event processing engine ensures that all threads are occupied to the fullest extent possible, giving you maximum utilization of your available CPU. So why put these all into one system? Streaming data often lacks context provided by stored data. Using fast data storage, your context data is co-located, so there's almost no latency in accessing it. You can then use that stored data as a source for a pipeline, or use it to store the results created by your pipeline, or use it for data enrichment as one of the steps in the pipeline. You can also program a pipeline to launch code, giving you another way to create reactive applications. Having these three capabilities combined into one platform has obvious performance advantages, which we've already discussed. However, the biggest advantage may be simplification. You have fewer integration problems and fewer things to monitor, resulting in a lower cost to operate. And your developers have fewer technologies to learn, resulting in faster time to market.